Sand is a key ingredient in solar panel production. However, the sand found in deserts and beaches isn't suitable for manufacturing these panels. Join us as we explore one of the most amazing transformations in the pursuit of renewable energy, turning sand into solar power. In this educational video, we will take you through the intricate process of manufacturing solar panels, from the raw material of silicon extracted from sand to the final product that harnesses the sun's energy. Learn about the different stages of production, including purification, crystallization, and assembly, as we break down complex concepts into easy-to-understand explanations. Solar panel manufacturing is a complex and energy-intensive process involving several critical stages. One of the biggest challenges is sourcing the high-quality raw material required for silicon, the key component of solar panels. Silicon is derived from one of the most common materials on Earth, sand. Also referred to as silicate or silicon dioxide, sand primarily consists of silicon and oxygen, the two most abundant elements on Earth. Most silicates on the Earth's surface are mixed with other elements like calcium, iron, and aluminum, giving them yellowish, tan, or other colors. These silicates are commercially utilized in producing glass and related products, including optical fibers for telecommunications and glass fibers for insulation. However, for more sensitive applications, such as semiconductors and solar cells, silicates that consist only of silicon and oxygen, known as quartz, are suitable. In this video, we will explore the significance of silicates, particularly quartz sand, in the manufacturing of solar panels. While sand is widely available, quartz sand is found in only a few locations around the world, such as the southeastern US and Australia, and it is extracted through open pit or underground mining. To obtain pure silicon, the mined quartz sand is mixed with carbon and heated in an electric arc furnace to temperatures exceeding 2000 degrees Celsius. At these high temperatures, the carbon reacts with oxygen to form carbon dioxide, leaving behind 98% pure metallurgical-grade silicon at the bottom of the furnace. Metallurgical-grade silicon is valuable in various industries, including steel and aluminum production. However, for solar cell manufacturing, even higher purity is required. Therefore, the silicon undergoes further refinement by mixing it with hydrogen and chlorine at extremely high temperatures, resulting in 99.9% pure silicon, the purity level essential for producing solar cells. A heated silicon rod or filament is immersed in the molten silicon hydrogen-chlorine compound, breaking the molecular bonds. This process allows silicon atoms to deposit onto the filament, while the hydrogen and chlorine atoms are recycled in a closed-loop system. Over the next few days, the silicon cools and crystallizes into a U-shaped rod, known as an ingot, with a purity of 99.9%. During this purification stage, a small amount of boron is added to dope the silicon, giving it a positive electrical charge. The U-shaped ingots are reshaped into rectangular forms because square-shaped cells can be installed more effectively later. Then, the ingots are sawed into thin discs known as wafers using a wire saw method, which minimizes waste and maximizes efficiency. These wafers are used to create two types of solar cells: monocrystalline cells, which are cut from the initial silicon ingots, and lower-efficiency polycrystalline cells, made from leftover silicon pieces that are molded together and resliced into wafers. Finally, the wafers are polished to achieve a smooth surface, preparing them for the next manufacturing steps. The production of solar cells begins with chemically texturing the silicon wafers. Texturing increases the surface area, enhancing the solar cell's ability to capture sunlight while also removing saw damage. After texturing, the wafers are doped with phosphorus, typically using a diffusion furnace. This process adds a negative electrical charge to the top layer of the wafers, creating a positive-negative or p-n junction, which is crucial for converting sunlight into electricity. Following doping, a thin layer of anti-reflective coating, usually silicon nitride, is applied to the top of the wafers. This coating minimizes sunlight reflection and boosts absorption. Then, metal conductors are screen printed onto each wafer, forming the grid pattern seen on solar cells. These conductors facilitate the collection and routing of the electricity generated by the cells through the solar panel. At a module assembly facility, copper ribbons plated with solder connect the silver busbars on the front surface of one cell to the rear of an adjacent cell in a process known as tabbing and stringing. Solar cells are interconnected in a series configuration to achieve the desired voltage and current characteristics. The interconnected cells are arranged between a tempered, durable glass front made from silica sand and a robust protective backing material, usually a type of polymer. Then, the entire unit is laminated in an oven to ensure the module is waterproof. Next, the assembly is fitted with an aluminum frame and edge sealant to protect the cells from environmental and mechanical stresses. A junction box and electrical cables are added to transmit the current generated by the module to the system's power electronics. The final stage of the manufacturing process involves testing and quality assurance to ensure that each solar panel meets specific performance standards and is free from defects. Panels undergo tests under simulated sunlight conditions to verify their efficiency and output. Those that pass all quality checks are labeled with their performance characteristics and certified for use. Although sand is plentiful around the world, the specific quartz-rich sand required for solar panel manufacturing is limited. As a result, optimizing the use of these resources is crucial for the sustainable growth of the solar energy sector. Since the 1950s, the efficiency of solar panels, defined by their ability to convert sunlight into electricity, has risen from 5% to over 20% today. Innovations such as bifacial solar panels also play a significant role, as they can capture light from both sides, generating up to 25% more electricity than traditional panels. Furthermore, recycling older panels can greatly improve efficiency efforts. If you're interested in exploring more about renewable energy innovations, be sure to check out our other videos and don't forget to subscribe, like, and share. Thanks for watching.